The second type, according to the same criterion, which is comparing the direction of propagation of the wave to the direction of vibration of the medium's particles, is the longitudinal wave. Consider the following example. If a spring is compressed at one end, this means that we are disturbing it, creating a disturbance. What happens after it is left free? The compression propagates through the spring, or the disturbance propagates through the spring, causing the particles of the medium to vibrate. The wave propagates from the left to the right, this means horizontally. And the particles vibrate also horizontally to the right and left. How can we tell that the particles are vibrating to the right and to the left? We mark a certain region of the spring by a red rope, small red rope, and we can observe in this way the rope vibrating horizontally to the right and to the left. So now if we compare these two directions, we can say that unlike the transverse wave, they are parallel to each other. So what can we conclude concerning the definition of a longitudinal wave? A longitudinal wave is a wave in which the particles of the disturbed medium vibrate parallel to the direction of the wave motion. Example, representations of a wave at an instant t. Longitudinal wave. So what are the vocabulary terms? Rarefaction is the region in a longitudinal wave in which the particles of the medium are further apart from each other, which means under low pressure. Compression is the region in a longitudinal wave in which the particles of the medium are closer to each other under high pressure. So consider the example. Let us observe and study the figure to the left side. If we compress the one end of the spring, then leave it, then after 1 second compress, then leave, then after 1 second compress, then leave. This means that you are repeating this disturbance periodically every certain specified period of time. Thus we create a periodic wave along the spring, and this periodic wave is a longitudinal wave because it causes the particles of the medium to vibrate in a direction parallel to the direction of propagation of the wave. So now, as you can see in the figure, the part or the region of the spring in which the coils are apart from each other under low pressure is called rarefaction, and the region in which the coils of the spring are closer to each other under high pressure are called compressions. Wavelength, symbolized by lambda. It's the distance a wave travels along its path during one cycle. So just like the transverse wave, for when a wave completes one cycle, it covers a certain distance called wavelength. In the case of longitudinal wave, the cycle must include a compression and a rarefaction. Why? Because for us to consider that a cycle is completed, the action or the behavior must be repeated identically. So if we take the compression alone and consider it to be a cycle, and look to the region just beside the first compression, the behavior is different. The coils are apart from each other. That's why we cannot consider one compression alone as a cycle or one rarefaction alone as a cycle. A rarefaction plus a compression form a whole cycle. And in the remark here we have that the distance between two corresponding points of consecutive rarefactions or compressions represent the wavelength of a longitudinal wave. So now, as we discussed for the transverse wave that there are three ways to find the wavelength using a diagram, similarly here for the longitudinal wave, we can either measure the wavelength by considering a whole compression and rarefaction as shown, in which we measure the distance from the starting point of one compression to the starting point of the consecutive compression, or from the starting point of a rarefaction to the starting point of the consecutive rarefaction. Now concerning the amplitude of a longitudinal wave. Consider a medium that's made up of the following particles. One particle is being marked by red in order to be able to detect its behavior and study it. Now initially at equilibrium, the particle is at the position of 3 meters away from the origin. So before disturbance. After a disturbance propagates through the medium and reaches this marked point, the point starts to vibrate horizontally to the right and to the left. So as you can see here in the second figure, in the middle one, the marked particle moved upward to the right to a maximum displacement, and this maximum displacement is marked by A, capital A. So the distance between this maximum position that the marked particle reaches and the equilibrium position is called the amplitude of the longitudinal wave. Similarly, for the other side, for the left side, the particle is going to reach a maximum point, and the distance between this maximum point and the equilibrium position represents the amplitude. In this case, the amplitude is equal to how much? Let's check the scale here. So this is the basic horizontal axis, and above is a zoom in for the scale. So they are showing you that from 0 till 0.5 there are how many subdivisions? 1, 2, 3, 4, 5. So every subdivision here, 0.5 over 5 is equal to 0.1. This means that every subdivision here represents 0.1. That's why in this case, being at 3.1 at x equals 3.1 for the maximum position, the maximum position at x equals 3.1 and the equilibrium position is at 3, then if we subtract them to find the distance between them, it's going to be 0.1 meter. So the amplitude in this case is 0.1 meter. Representation of a wave at an instant t. So again, talking about the longitudinal wave, the amplitude is the maximum increase or decrease in pressure from the equilibrium pressure that is caused when a compression passes a point. So when you find for the longitudinal wave, the point here at x1, at position x1, is under the maximum pressure. So that's why if you want to represent the variation of the pressure as a function of position, we find that x1 corresponds to a maximum point. Then as we move away from x1 till x2, the pressure starts to decrease. That's why the graph here starts to decrease until we reach a particle at position x2 in which the pressure is the lowest. That's why x2 corresponds on the graph to the lowest point. An analogy between the transverse and longitudinal wave is the following. A transverse wave in a crest corresponds to a compression in the longitudinal wave, because the crest in a transverse wave corresponds to the maximum displacement, and the compression in a longitudinal wave corresponds to the maximum pressure. The trough in a transverse wave corresponds to the lowest point or the lowest displacement, and the rarefaction in the longitudinal wave corresponds to the lowest pressure. The amplitude in both cases is the maximum displacement with respect to the equilibrium position. And concerning the graphs, if the graph shape is as such, like a wave, and you have displacement versus x on the displacement on the y-axis versus x, then this corresponds to a transverse wave. But when we study the pressure as a function of x and the graph is as such, then this corresponds to a longitudinal wave. Application on longitudinal wave. A couple of loops of a spring were compressed, then released freely. A snapshot of the spring at a particular instant after the release is represented in the figure below. So explain what happens after compressing and releasing the loops. Upon compressing the loops, a disturbance is produced. Then releasing the loops, the disturbance propagates through the spring, thus causing the vibration of other loops. In other words, a longitudinal wave is produced. Calculate the wavelength of the produced wave. We can either measure it from the beginning of the compression to the beginning of the consecutive compression as shown for the red arrow, which is 0 till 5 centimeter, or from the starting point of a certain rarefaction to the starting point of the consecutive rarefaction, and we're going also to obtain the same value, 5 centimeter.